I'm Johnny Alonzo. You may recognize me from my role as Jimmy on Dawson's Creek. Now, on today's episode of NASA Sci Files, there's going to be a whole lot of shaking going on when the Treehouse detectives use science, math, and technology to reveal the secrets of earthquakes. So stay tuned and hold on for this exciting episode of NASA Sci Files, the case of the Shaky Quake.
On this segment of the case of the Shaky Quake, you'll be asked the following questions. What is a seismologist? Describe the layers of the Earth. What are two types of clues that help us learn about the Earth's history? And when you see this icon, you will know that the answer is near.
I think this bone goes right here. I think it's part of the tail.
Wrong, it's actually part of the head.
I guess so. But this is the closest that we're gonna get to a dinosaur dig.
Jacob is gonna have so much fun looking for dino bones.
Excuse me? They're called fossils.
Did you feel that?
Huh?
I did. What could it be?
I felt that one.
Now that you're with us, what do you think it is?
It's an earthquake.
Don't jump to conclusions. Go to the NASA Sci Files website to see if they have any information on earthquakes. Visit the research rack on the NASA Sci Files website for resources on earthquakes.
I found two places in Virginia where seismologists record earthquakes.
A size what?
A seismologist is someone who studies and measures earthquakes.
Look, I found a seismogram located near us at Tidewater Community College. Let's call seismologist Michael Lyle.
Michael Lyle, Tidewater Community College, Seismology Lab.
Hello, Mr. Lyle. Tony D'Angelo, Treehouse Detective. I would like to inquire if your instrument picked up a tremor a few minutes ago.
Yes, our seismograph did detect something.
Was it an earthquake?
Maybe, but it's not clear from my reading here.
Okay, we'll check back with you. Mr. Lyle says there's a very good possibility there's been an earthquake. Maybe I exaggerated a little bit.
We all know it's going to take a lot more research to solve this problem. Look, here's an update from KSNN.
I'm Ted Toon with this Kids Science News Network special report. Strange vibrations in the area have local residents concerned. We've sent our reporter, the usually unshakable I Am Listening, outside to look around. I Am?
Well, Ted, I'm outside. I don't see anything.
Well, I Am, don't get shaken up. Why don't you look around a little?
Mostly because it's starting to rain, Ted. I'm coming back in.
I Am? I Am. And she calls herself an investigative journalist. Anyway, that was I Am Listening with a live... Wow!
I'm glad we're not the only ones who felt the vibration.
I think there's sufficient evidence to show that we need to launch an official investigation.
In simple words, let's go to the problem board.
We know we felt the shake. TCC recorded something, and KSNN reported a mysterious vibration.
Since we're pretty sure it's an earthquake, I think we need to...
Wait a minute. We need to do a lot more research before we come to that conclusion.
Okay, so we need to do more research on earthquakes. They'll say I'm correct.
I think we need to know what else causes vibrations.
I'm sorry, what did you say? I was calculating the cost of remodeling the treehouse to make it earthquake-proof.
Tony, we don't even know if it was an earthquake, and we sure don't have enough information to know how to make a treehouse earthquake-proof.
I estimate that it would cost about $20,000, and if we took out a loan with an interest rate of 6.5% for 30 years, then our payment would be $128 a month for principal and interest. Okay, let's get back to the problem. Dr. D's from California. I'm sure he's been in a few earthquakes. Hi, Dr. D.
Hi, guys, what's up?
We felt our treehouse shake this morning and wanted to know what happened.
Yeah, I felt something too.
We think that it might have been an earthquake, but we can't prove it yet.
Have you ever been in an earthquake?
Yes, I have. But it didn't feel the same as what I felt this morning.
See, I told you it wasn't an earthquake.
Well, wait a minute. All earthquakes don't feel the same. To begin understanding earthquakes, you have to know something about the structure of the earth.
That makes sense. What can you tell us?
Come on, let me show you.
Okay.
Let me cut this peach in half.
Okay, be careful.
I will, thanks. This will be our Earth.
Only it's a lot smaller.
It's called a scale model. The pit is like the core of the Earth. The Earth's core is about half of its diameter.
What's it made of?
We've never been there, but we think it's made of iron and nickel. The inner part of the core is solid, and the outer part is liquid. It is so dense, if we had a gallon jug full of the Earth's core material, it would weigh over 100 pounds.
Wait, Dr. D, you lost me. How do we know how big the core is and what it's made of if we've never been there?
Well, it's just a guess.
You're kidding.
Well, actually, it's a pretty good guess based upon a lot of evidence. One of the biggest clues we have to the structure of the Earth comes from our study of earthquakes.
So we're using earthquakes to help us understand earthquakes?
That's right. The part of the peach that you eat is called the Earth's mantle. It's not as dense as the core, but it's more dense than what's on the outside.
What's the outside called?
It's called the crust.
Just like the crust of a bread.
Very good. Like the skin of a peach, the Earth's crust is very thin. The crust under the oceans is typically between 5 and 10 kilometers thick. It's made of a dark, dense rock called basalt. The continental crust is between 30 and 70 kilometers thick. It's made of a lighter, less dense rock, like this granite.
Is there a reason why the Earth is layered like this?
It's because of density. Watch this experiment over here. I'm going to put this green-tinted water and this salad oil into this graduated cylinder and then shake them up. Let's see what happens.
The salad oil is on top, and then the water.
Let's put in some motor oil. It turns out the least dense, which is motor oil, floats on the top. And the most dense, water, sinks to the bottom. It's just like the early history of the Earth, when it was all liquid.
Earth? Liquid? Strange, but what does this have to do with earthquakes?
When the Earth cooled, the crust upper mantle became rigid and brittle. They broke into about 12 segments, which we called plates, kind of like this cracked boiled egg. These plates float on the more dense but flexible mantle below, kind of like this egg white. These plates are in continual movement.
Wow, this is too weird. Why do we feel them moving?
They move about as fast as your fingernails grow, which is only a few centimeters per year. But we have fossil evidence of this movement, which we call plate tectonics.
Are fossils also clues to understanding earthquakes?
Well, yes.
But Dr. D, aren't there other things that could cause vibrations?
Well, yes, that's a good question. Anything that makes a very loud sound can make things shake a little.
I watched fireworks on the 4th, and some were so big, I did feel a vibration.
Oh no, I'm late for an appointment. Why don't you stay for a while and discuss this amongst yourselves?
Okay, bye, Dr. D. Let's go over there and discuss this. What about a sonic boom? We learned from the case of the barking dogs that a sonic boom is created when a plane travels faster than the speed of sound.
That's it. It's our hypothesis. If there are airplanes flying faster than the speed of sound, then it'll cause the ground to vibrate.
I don't think a sonic boom is our hypothesis. I forgot my dad says that the military never flies faster than the speed of sound over land anymore.
Oh, I thought we had it.
I'm glad RJ and Jacob are going to California for the science fair. Maybe they can research earthquakes for us.
Wait a minute. Jacob is in Utah looking for fossils. Dr. D said there's fossil evidence of plate tectonics.
I wonder if that's the same thing as the continental drift theory my teacher talked about.
Maybe, but I don't understand what fossils have to do with plate tectonics or earthquakes.
Let's email Jacob and see if he can find the answers for us.
Okay, I'll do it.
We need to do some research on our own. Let's go back to the treehouse and find out if anyone else has felt the vibrations.
this is amazing. This is so cool. I can't believe I'm touching a dinosaur bone. Is this real?
Yes, it is. Hi, I'm David Whitman. I'm a park ranger here. And these bones are 150 million years old.
Wow.
Want to see something really neat?
Yes.
Follow me.
Amazing. I've never seen anything like this. Did you just put these bones in the wall?
No, we didn't. Excavation started here in 1909 and ended in 1990. We're doing excavations elsewhere. But during that period of time, we uncovered over 1,000 dinosaur bones.
How did they all get here?
A lot of them died of natural causes, and some of them died when the river dried up and they didn't have enough water.
Oh, I almost forgot. My friends wanted to find out for sure if fossils are clues towards plate tectonics and earthquakes.
Oh, I can help you with that.
I have lots of questions. What was the environment like?
Well, this was the bottom of a river, and the area was flat, arid. There were a lot of plants growing along the rivers, and of course that's where the dinosaurs congregated.
Another question. How warm was the climate?
It was hot year-round, and the reason for that was that this area was a lot closer to the equator 150 million years ago. So over the last 150 million years, because of plate tectonics or continental drift, this area has moved northward 400 miles.
It's hard to believe that land can actually move that far. I read in a book once that no one believed Alfred Wagner in the early 1900s when he proposed the idea known as continental drift. What is continental drift?
It was a theory that stated that the continents were once one large landmass called Pangaea. Clues indicate that in the last 200 million years, the continents have moved or drifted horizontally to their current locations. The revised theory called plate tectonics explains why continents drift. Continents are part of large plates that move across the Earth's surface and bang into one another, causing earthquakes and pushing up mountain ranges.
You mean fossil clues?
Yes, fossils can be clues to continental drift. For example, fossils of the reptile Mesosaurus have been found in South America and Africa. These reptiles live in freshwater and on land, so how could they be found on different continents unless the continents had one time been together? Well, another clue can be found in rocks.
Strange. How do you know that a rock found here is the same as another rock found in the Colorado Plateau?
Well, why don't you come with me? We'll take a walk and find out.
Great.
Well, Jacob, this is the Green River.
Wow. I know I'd never seen anything like this before.
As you can see, there's lots of different kinds of rocks here. Rocks can be clues of continental drift, but that's not the case here.
They all look the same to me. How can you tell the difference between rock structures?
Well, it's like a detective story. We look over at this sandstone over here. It looks like 6 other types of sandstone that we have in the monument. So how do we tell the difference? We have to look at the rocks that are associated with it. If we look at the rock that's just below that sandstone, we can tell it's the Chinle Formation. Chinle looks the same all across the Colorado Plateau. So now we know the rock above it, this sandstone, is the Glen Canyon sandstone.
Do you have earthquakes here?
Here, earthquakes are caused by mountain building forces. So 65 million years ago, as these flat rocks were being pushed up into an arch, earthquakes occurred. If you've ever seen a cake in an oven, it'll rise and rise and rise, but at some point, what happens to the cake if it rises too much?
It has to sink back down eventually.
It'll collapse. Well, the same thing happens with rocks. They'll be bent, but they can only bend so far, and at some point, they'll eventually break.
And when the rocks break, is that what causes an earthquake?
That's correct. That break is the fault line, and when the rocks move along the fault line, it creates an earthquake. Well, have I answered all your questions?
Yeah, I can't wait to go email the treehouse detectives.
Well, do you have some time to go look for some fossils?
Sure.
All right, let's go.
So what's up? Will fossils help the treehouse detectives solve the mystery? Do you think the treehouse detectives experienced an earthquake? What else could have caused the vibration? Stay tuned for the next exciting chapter of The Case of the Shaky Quake.
Try to answer these questions for the next episode of The Case of the Shaky Quake. What are 3 types of faults? What are 3 types of plate boundaries? How does a seismograph measure the shaking of the Earth?
That was was my last call. A lot of people on my list said they felt a vibration. We received a lot of emails. Some people say it felt like an explosion.
Let's email KSNN and ask if there are any reports of an explosion in the area.
Maybe this is our new hypothesis. If there was an explosion, then it would cause the ground to vibrate. I was talking to one person who said it felt like a heavy truck driving by.
There's also an email describing it as a sonic boom, but we know it's not a sonic boom.
Here comes an update from KSNN. I wonder if they received our email.
This just in. The Treehouse detectives have raised this question. Were there any explosions that could account for the vibrations detected yesterday around noon? For the answer, we go to I Am Listening on the scene.
Ted, we're here at the site of the new Mega Bulk Mart. Yesterday at exactly 12 noon, the original This Little Piggy barbecue restaurant was demolished to make way for construction. We have this exclusive videotape sent to us by Mr. Flange Lugnut. There you have it, folks. The tremors felt yesterday were simply gigantic explosions. Nothing to worry about. Back to you, Ted.
I Am is obviously not a scientist. Doesn't she know you just can't jump to conclusions? You must do research.
Cool, that confirms my hypothesis. Look at our clock. It stopped at noon, so they must be the same explosions. That's what I call using my observation skills. Observation is an important part of the scientific process.
You're like I Am, jumping to conclusions. I still think it could be an earthquake, and I don't want to take any chances.
Maybe Tony is right. Jacob sent his email from the Dinosaur National Monument that the movement of the Earth's crust and upper mantle, called plate tectonics, causes earthquakes.
I'm reading more about plate tectonics in my Earth Science book. It says the crustal movement occurs along fault lines. Maybe we should learn more about faults.
Let's do an internet search. I'll go to a search engine and type in the words earthquake, faults, and Virginia.
Finding anything?
The search shows several websites for the United States Geological Survey, or USGS. Let's go to their homepage.
I heard they monitor earthquakes all over the U.S. It sounds like they'd be able to help us.
I clicked on California on the map, and they have an office in San Francisco. Let's email Jacob and RJ and ask them to talk to the USGS.
Ready, RJ? Hey guys, I'm here at the San Andreas Fault, near where the epicenter of the 1906 San Francisco earthquake occurred.
Hi guys, you must be the Treehouse detectives. How can I help you?
Our friends in Virginia felt a vibration the other day, and they wanted to find out if it was an earthquake.
They said we needed to learn more about faults.
Well, a fault is a weak zone in the Earth's crust where the rock layers have broken and slipped apart. Would you like to see the San Andreas Fault?
RJ, be sure and get me on camera.
Okay. So where's the fault line?
You can see it here. See the line that goes up the wall?
Are there different kinds of faults?
Yes, there's three kinds of faults. One is called a normal fault, and that's when the fault is at an angle and the top block is called the hanging wall, and that moves down relative to the lower block called the footwall. And this happens where there's extension in the crust and it pulls apart.
Is there an abnormal fault?
Well, it's not really an abnormal fault, but there is a fault that's opposite of a normal fault, and that's when the hanging wall block moves up relative to the footwall block. And this happens where there's crustal compression. And those faults are called reverse faults or thrust faults.
What's the last type of fault?
Well, the last kind of fault is called a strike-slip fault, and that's like where we are now on the San Andreas Fault.
We learned that the Earth's lithosphere is broken up into plates, and the plates' movement is what causes earthquakes. But I don't get it. Are plates and faults the same thing?
Well, moving plates grind and scrape against each other at their edges, and those edges we call plate boundaries. And plate boundaries are usually made up of mini faults.
Are there different kinds of plate boundaries like there are different kinds of faults?
Yes, there's also three of those. Divergent boundaries are where the crust is being pulled apart. This can form new crust or cause rift valleys and even make volcanoes. The pulling apart can happen at about 2 centimeters a year.
That's not very much. It must move really slowly.
Yeah, they do. And a convergent boundary is where the plates crash head on.
Oh, those boundaries move slowly too.
Yeah, they do. They only move a few centimeters a year, and because it's slow, it can take millions of years for them to form. And when the plates collide, sometimes you can get large mountain chains like the Himalayas.
Wow, now I'm starting to understand why the Earth is shaped the way it is.
The last boundary is called a transform boundary, It's when plates slide past each other, like the San Andreas Fault here.
Does that mean California's not going to break off and fall into the ocean?
No, that's a common misconception. Actually, Los Angeles may someday be next to San Francisco, but that will probably take 10 million years.
That's a long time.
I don't think we have any boundaries in Virginia. Do earthquakes occur anywhere else?
Yeah, a few earthquakes occur in the middle of plates, called interplate earthquakes. And in 1886, there was a large earthquake in Charleston, South Carolina.
South Carolina is near Virginia. Maybe they did have an earthquake.
Do you want to try making your own earthquake?
Will it knock houses down?
No, it won't be a real earthquake. It'll just be a simulation of a very small one. Let's go. I have a setup here that we're going to pretend is like the Earth's plates moving. So you're going to turn the crank and apply stress to these blocks. You're going to cause a force to be pulling them. And this is going to be the equivalent of one plate, and this is going to be the equivalent of another crustal plate. And watch as you add more and more stress and see if you can get an earthquake.
RJ? Wow, was that an earthquake?
Yeah.
Now that's my kind of earthquake. This has really been helpful. Thank you.
Sure. Well, email me if you have any more questions.
Okay.
Done. Do you know what kind of dinosaur this is?
Yeah, it's a Tyrannosaurus Rex.
Not bad.
What's going on? I don't know, but I don't like it.
Now that was an earthquake.
How do you know?
Just felt like one.
Maybe it was another construction blast. I'll call KSNN.
Do you think an earthquake could affect the stock market?
Listen, right now, we have bigger problems. KSNN just confirmed that there were no reports of a construction blast.
I don't know, but we need to organize our thoughts. Let's go to the problem board.
We know we've had a few tremors. We know that KSNN said the first set of tremors was from a construction blast, and the second was not.
We know that the structure of the Earth is divided into layers.
We also know the Earth's crust is divided into plates, and these plates can move and cause earthquakes.
Oh yeah, remember that email from Jacob and RJ? They talked to Miss Heidi Stenner, who confirmed that there are a lot of faults in the Earth's crust.
Now we need to know if there are any faults in the area that could cause tremors.
I think we need to visit the seismologists at TCC to find out if there are any faults in our area. We can also see if they recorded another tremor this time. Let's get up and go.
I think we're closer to figuring out if this vibration was an earthquake.
This must be a seismograph. I recognize it from TV. I wonder if Mr. Lyle is here.
Oh, hi, Mr. Lyle.
Hi, girls.
We're the Treehouse Detectives. We called you about an earlier tremor. Now we need to know if you've recorded anything on your seismograph today.
As a matter of fact, we did, and here it is right here.
Wow, was that an earthquake? Can you really tell from that reading?
We're not sure at this time. We're analyzing the data because not all detected tremors are related to earthquakes.
Analyzing your data is very important in the scientific process.
In this area, most of the tremors we detect are relatively small, travel a short distance, and generally occur between 8 a.m. and 5 p.m. This suggests that they're caused by human conditions.
We learned that there are earthquakes because there are breaks in the Earth's crust that are moving along fault lines. Are there faults in Virginia?
Yes, there are numerous faults in Virginia, but not all of them are active faults.
Wow, does Virginia have a lot of earthquakes?
Not really. In the last 30 years, there have been more than 150 earthquakes in Virginia. But these are low-intensity events, seldom felt by people.
Where do most Virginia earthquakes occur?
Most seem to occur in the central and western part of the state.
We don't live near that part of the state. What other things could cause a reading on your seismograph?
Anything that shakes the ground can be recorded. Here's a seismogram, or paper recording of that construction blast from the other day.
It looks so small, but it created such a big boom.
Our seismometer, measuring instrument, is very sensitive. This is what automobile traffic and even storm waves from a beach look like.
That's pretty neat.
The seismometer is buried 70 meters below us. It is so sensitive that we had to put it in a very quiet place.
That's way down there.
Would you like to see a seismogram of a confirmed earthquake?
Yes. What are the little square marks?
How can you figure anything out?
You guys have lots of questions. Well, every square ticks off a minute.
Oh, so you can tell when an earthquake happens and how long it lasts.
That's correct. To most people, these look like squiggly lines, but when I look at them, I see S&P waves.
Like sound waves.
They are somewhat like sound waves. These are vibrations in the earth.
That doesn't look at all like the tremor we felt. Does that mean it wasn't an earthquake?
Not necessarily. A local earthquake could look very different from this.
We need one of these in our treehouse. Then we could measure the next tremor.
I think Dr. D is down the hall building a seismograph.
Dr. D, a seismograph? We're there. Hi, Dr. D.
Hi, kids.
Is this the seismograph you're building?
That's right. I'm almost finished. This seismograph is not very sensitive, but it does work. It measures horizontal motion.
So you actually use a peanut can and an old brick?
Yeah, sure. Let me start from the beginning. The seismograph measures the shaking of the earth. To measure the shaking, we take advantage of Newton's first law.
I think I remember. Isn't it also called inertia?
I'm impressed. So what is inertia?
It means that when an object is at rest, it stays at rest. And when an object is in motion, it remains in motion.
That's right. This brick has a lot of inertia, so it's hard to get moving. When the earth shakes, the base of the seismograph will also shake. But the brick, which is not tied to the base, will not. The pen over there records the vibration.
Can we try it?
Sure, let's make an earthquake by shaking the table.
It really works. Look at the waves. Did we do that?
You sure did. Here's a different kind of seismograph. It measures vertical motion.
It looks really different.
Because it has inertia, this magnet hanging on the spring tends to stand still when the table moves up and down. A magnet moving through a coil of wire produces electricity, which this meter records.
Can we try this one too?
Sure. All right, but here's a sensitive seismometer that's hooked up to this computer.
That graph looks a lot like the seismogram that Mr. Lau showed us.
The harder I hit the table, the larger the signals. This is really cool.
And look at how it vibrates, up and down.
Because it produces an electric signal, it is easy to amplify. Even a small vibration can be shown on the computer. Now, I can't loan you this device, but why don't you take my wooden seismograph back to the treehouse and see if you can record another tremor? I have a friend at NASA's Jet Propulsion Laboratory in Pasadena, California, who uses satellites to measure the motion of the Earth's crust. You might want to talk to her in your quest to become earthquake experts.
So what's up? Will the seismograph help the treehouse detectives solve the mystery? Will satellites provide the answer? Stay with us for the next exciting chapter of The Case of the Shaky Quake.
Can you answer these questions? What is GPS and how is it used? What are SMP waves and how do they differ? What are two types of scales used to measure earthquakes? I'm not so bad.
What?
I'm looking at my soccer journal, and so far in my soccer career, I've scored 282 goals and attempted 670. That means that my shooting percentage is 42.1%. That means I score a goal about half the time. See, you do use math in sports.
Okay, getting back to business, this is a homemade seismograph on loan from Dr. D. Now we'll be prepared in case there's another tremor.
I don't know if I would depend on that machine. It looks rather weak.
But maybe this instrument isn't the only way to detect earthquakes. Remember Dr. D told us about JPL and how they monitor crustal movement using satellites. He gave me the name of his friend, Andrea Donnellan. Let's dial her up.
Hi, we're the Treehouse Detectives. Dr. D said that you might be able to help us learn about how crustal movement is monitored.
I sure can. I use GPS to measure crustal movements.
I've heard of GPS, but I'm not sure what it is or how it works.
GPS stands for Global Positioning System. It's a satellite navigation system consisting of 24 satellites. Pilots and boaters use it to plot their course. Geologists use it to accurately measure the position of monitoring stations. Here in Southern California, we have a network of 250 GPS stations.
How does knowing the position of these stations help you to understand earthquakes?
It shows us the stretching, warping, and movement of the crust that's not really noticeable.
How accurate is it?
We can measure the positions of points on the Earth to 3 millimeters horizontally and 7 millimeters vertically.
That's small. How does that differ from what a seismograph does?
A seismograph measures earthquakes when they happen. With GPS, we can actually measure the quiet motions of the Earth. That means we can measure the strain buildup as well as the earthquakes themselves. It is particularly useful in identifying active blind faults.
What's a blind fault?
A blind fault is a break in the crust that doesn't break through the surface anywhere. Naturally, these faults are not easy to locate or study and might go unnoticed without GPS technology.
That's pretty impressive. I'm glad we have the ability to see these faults. Will this technology help us to predict earthquakes?
We are integrating data from a lot of different sources into computer simulations. These simulations should help us understand the earthquake process. We hope to eventually be able to do short-term forecasting.
Can you give us an example?
By monitoring all the stations, we can find out which faults have the greatest slip rate. The slip rate, typically measured in millimeters per year, is how fast the two sides of a fault are moving past each other. These faults that have the greatest slip rates may be the locations of future earthquakes.
I wish you were able to make a prediction now. Can GPS help us to know if we experience an earthquake in Virginia?
We can use GPS to measure displacements from earthquakes, but we don't measure the shaking part from an earthquake. The seismometer is used to measure this, and it will be better able to answer your question.
Thank you very much, Dr. Donnellan.
You're welcome. Email me if you have any questions, and say hello to Dr. D for me.
Cool. I can't believe that the GPS can detect 3 millimeters of movement from space. Check this out. Come closer. 3 millimeters is only this much.
Hi, Tony. We're talking about GPS. In the future, it might help us to predict earthquakes.
Yeah, that's great, but what about the problem right now?
Dr. Donnellan said that if there was an earthquake in Virginia, seismographs would pick it up.
But we looked at a few seismograms and we still don't have a definite answer. Let's do some problem solving.
I have an idea. Why don't we call RJ and Jacob?
Tell them hi. I've got to go. I've got soccer practice today. Bye.
Hi, guys. How's California?
It's great. Look at the Golden Gate Bridge behind us. And we're learning a lot at the science fair.
So, are you still trying to solve the tremor problem?
Yes, but we need your help with the problem board.
Okay, let's go to it.
Well, we know the first set of tremors was not related to the second.
We know the plate's movements can cause earthquakes, and that there are a lot of faults.
We know there are faults in Virginia.
And we also know that other things can cause movement on the seismograph.
Like what?
The seismologists told us that core blasts, sonic booms, and thunderstorms can often be mistaken for earthquakes.
Thunderstorms? Did we have storms that day?
It was cloudy and stormy that day, but I don't remember seeing any lightning.
But it did sound like a clap of thunder, and that will register on the seismograms. And earthquakes don't make noise, so it must be thunder. Maybe this is our new hypothesis. If there was thunder, then it would cause vibrations on Earth.
Don't throw away your earthquake hypothesis too quickly. During my vacation, I've been doing a lot of research on earthquakes. And look, I just happened to find this account of an earthquake in Oklahoma. And here it is. I heard something like a loud clap of thunder, or something exploding.
Great job, guys. Our competing earthquake hypothesis still survives.
I still think that we need to know if there was thunder and lightning that day.
We never checked out what the seismologist said about S&P waves. I think we should. It might be a clue. See you guys. Have fun with Dr. D.
Hey, Dr. D.
Hi, guys. Good to see you here in San Francisco, California. I understand from the email that you want to know more about earthquake waves.
Yes.
I put together some demonstrations for you.
Great.
Let's talk about 3 different kinds of waves. The first 2 are S and P waves. They're called body waves, but they travel through the body of the Earth.
Mr. Lyle showed the other treehouse detectives those on the seismogram.
Well, P stands for primary or compressional waves, and S is for secondary or shear waves. P waves make the Earth vibrate back and forth along the direction of motion. Let me show you with this slinky over here.
Those don't look like the waves I'm used to seeing, like ocean waves.
The wave you're used to seeing has up and down or side to side motion. This is like the shear wave or S wave. Looks like this. Another important difference between S and P waves is that P waves travel faster than S waves, almost twice as fast.
I guess that means that P waves will always arrive first.
That's right, and the difference in time between the arrival of the S and P waves can help us find the epicenter of the earthquake.
What's an epicenter?
It's the point on the Earth directly above the focus, or the point where the earthquake originates. Have you ever heard about counting the seconds between seeing the lightning and hearing the thunder?
I have, but I've never done it.
Well, it works because light and sound travel at different speeds. For example, when you see the lightning, start counting.
1001,
1002, 1003.
The sound arrived about 3 seconds after the lightning. That means the lightning is about 1 kilometer away. For earthquakes, first you'll feel a P wave, and then seconds later you'll feel a more powerful S wave. For local earthquakes, every second that you count means you're about 8 kilometers further away from the epicenter.
I don't think I'd be counting the seconds if I was in an earthquake.
don't think I would either. Now, the third and slowest of these waves, the surface wave, is the most destructive of them all. Here in California, they have to build structures to withstand these dangerous waves.
How do they know how to do that?
One way is for engineers to use shaky tables like these, only much bigger, to test their designs. Let's try it out.
I'll bet my structure can withstand the greatest earthquake.
We'll see who's the best engineer. I guess we have a little bit more to learn about the power of earthquakes.
Dr. D, didn't you say we could experience an earthquake here at the museum?
You need to go see my friend, Dr. Tang.
That must be the earthquake theater. I hope it's not like the hurricane room that Bianca and Catherine went to.
Treehouse Detectives?
That's us. Nice to meet you, Dr. Tang.
I hear you're interested in experiencing an earthquake.
Well, I don't know about that, but we do need to learn more about how experts measure the power of earthquakes.
One such scale is called the Richter Scale. It tells us the strength of an earthquake.
Are there other scales that scientists use?
Now scientists prefer a more precise scale called the moment magnitude scale. It's a number that tells us about the energy released from an earthquake.
What's the number of our earthquake?
Well, if it was a quake that people could feel, it must be at least a 2. A moderate earthquake is about a 5.
Wasn't there a major earthquake here in San Francisco in 1906? What was its number?
It was a 7.7, but to understand what that means, you really ought to experience the earthquake.
I'm not sure I want to do that.
Don't worry, it's quite safe. We're going to be doing it here in the Earthquake Theater at the California Academy of Sciences.
Don't forget to bring the camera.
I got it.
The San Francisco Bay Area experienced a powerful earthquake.
Cool. It seems so real. How do scientists know so much?
Well, we looked at people's diaries and also had houses and churches that were damaged during the earthquake, and also how the earthquake ruptured the ground around San Francisco during the time period.
I guess observations are important. Your science journal might be valuable evidence one day.
Yes, we'll take a look at this earthquake questionnaire. You'll see that even today, even with sophisticated instruments, scientists still depend on people's experiences to understand earthquakes.
Wow, look at this. They want to know if it was difficult to stand or walk.
And did objects rattle or fall off the shelf?
Here's a simple question. What's your zip code?
Does it make a difference where you live?
Yes, the effects of an earthquake vary greatly depending on how far away from the source you are.
You mean the farther away you are, the less shaking you feel from a quake?
Yes, but it also depends on what the ground is like.
What does the ground have to do with it?
Well, let's take a look at this gelatin. If I push on even a little bit, it jiggles a lot. And yet, if I take a rock, no matter how hard I push on it, it's not going to jiggle at all.
I know where I would want to stand during an earthquake. Solid rock.
That's right. Houses built on mud and sand don't do so well during an earthquake.
Thanks, Dr. Tang.
You're welcome.
So what's up? Could a thunderstorm have caused the tremor? Will S&P waves help solve the mystery? What should the Treehouse Detectives investigate next? Don't miss the exciting conclusion of The Case of the Shaky Quake.
In the conclusion of the case of the Shaky Quake, see if you can answer these questions. How many earthquakes occur each year? How many seismic stations are necessary to pinpoint the epicenter of an earthquake? What are the differences between meteors, meteorites, and meteoroids?
Why are you so down?
I called the weather service and they said they didn't record any lightning strikes in our area on the day we felt the last tremor.
Maybe I shouldn't mention that I called another seismologist at Virginia Tech, which is about 300 kilometers away, and their seismograph picked up something around the same time that we felt the tremor.
So that doesn't mean my thunder hypothesis is wrong.
It might. Think about it. The seismologist said it was clear that day. no thunderstorms in sight.
Well, Mr. Lau said his seismograph only detects local thunder. Well, maybe you're right.
The seismologists also said that eyewitnesses reported seeing a fireball in the sky, and they heard a loud noise.
I don't remember seeing a fireball that day. Here comes Dr. Textbook.
Hello! Dr. Textbook here with some earth-shattering facts. You'll never guess how many detectable earthquakes there are in the world each year. Try 500,000, that's 500,000 earthquakes a year. Californians, listen up. Every year the southern part of California has 10,000 earthquakes, but most of them are not felt. Yee-haw! Now, which state is the most earthquake prone? Not California. Try Alaska. It has a magnitude 7 earthquake every year. And here is a trick question. Is there such a thing as earthquake weather? No, earthquakes happen in the cold, in the rain, and in the heat. Now, let's see if we can feel one of those 500,000 earthquakes. Not a very good idea.
Earthquakes are like hurricanes. They're so powerful and can be so deadly. Look, we have an email from Jacob and RJ. They say Dr. D told them about how to use PNS waves to find the center of an earthquake.
Dr. D says you must have 3 seismic stations to locate the epicenter.
We have 2. Maybe that's enough. I doubt it, but I have an idea. Let's write the Sci Files Kids Club and ask them if they know how to use S&P waves to map an epicenter. Hey, we have a response from Roberts Park Elementary School in Norfolk, Virginia.
Hi, we're from Mr. Darrell Ransom's 3rd grade class at Roberts Park Elementary School in Norfolk, Virginia.
Hi, we're the Treehouse Detectives, and we see you're doing an activity to find out where an earthquake occurred. Could you tell us something about it?
Sure. Our mentors from the Society of Women Engineers helped us with the activity called triangulation.
It must have something to do with threes.
Yes, we learned that in order to find the origin or epicenter of an earthquake, we needed data from 3 different seismic stations.
Did you need any special materials?
No, just a world map, a seismogram, a graph, and a drawing compass.
What did you do next?
First, we looked at the seismic recordings and determined when the S and P waves each arrived at the seismic stations.
How could you tell which one was which?
We know the P waves travel faster and arrive first. We then found the difference between the 2 times in seconds. For example, at the Denver, Colorado station, the P waves arrived at 10 hours and 16 minutes, and the S waves arrived at 10 hours, 18 minutes, and 30 seconds.
I know, the difference was 2 minutes and 30 seconds.
That's correct. We then used the graph to mark off 2 minutes and 30 seconds along the edge of the piece of paper. We slid the paper along the graph between the S waves and the P waves to find the distance in kilometers that the waves had traveled.
How far did the waves travel?
About 1,600 kilometers. After finding the distance the waves traveled, we located the city on the map. We used the map scale and our drawing compass to measure that distance. We placed the point of our compass on the city and drew a circle.
Why a circle?
We know that the earthquake occurred 1,600 kilometers from Denver, but that could be 1,600 kilometers in any direction. So we used 1,600 kilometers as our radius, and the earthquake occurred somewhere along the circle.
How do you pinpoint the location?
We repeated the steps with the next seismic recording for Terre Haute, Indiana.
But the 2 circles intersect at 2 different points. How can you tell which one is the epicenter?
That's why you need a 3rd seismic station. Once all 3 stations are plotted on the map, you find where the 3 circles intersect. The intersection is the approximate epicenter of the earthquake.
Well, they answered one question for us. We really do need 3 seismic stations, not 2 to map out the epicenter.
Is the earthquake our only hypothesis?
It is for me. Just joking. I think we need more conclusive evidence to show that it was an earthquake.
Will this help?
RJ, you're back.
I have this DVD of Jacob and me in an earthquake.
You were in an earthquake?
Well, sorta. But really, it was an earthquake room.
That doesn't look like what we saw at our treehouse.
This case isn't as easy to solve as the others.
No one will confirm that it's an earthquake, not even a seismologist.
Let's call another seismic station to see if they picked up a tremor on their instruments. Maybe that'll help confirm it.
I don't know why, but I think it's something else.
Here comes KSNN. Maybe they have some more information.
Ladies and gentlemen, we are continuing to investigate the recent tremors. It seems that the quakes felt by our viewers may have had different sources. For more, we go live to I Am Listening.
Ted, I'm here with esteemed scientist Dr. Liz Ard. Dr. Ard, what can you tell us about the events of yesterday?
Well, we have received vibration reports from cities all along the East Coast. Many people also saw a fireball, which we now believe was a meteor entering Earth's atmosphere. Our tracking cameras were able to record this image before the meteor flew out of sight.
Amazing! Thank you, Doctor. Back to you, Ted.
Well, folks, those vibrations were merely giant explosions and huge meteors falling from space. Nothing to worry about. Nothing at all. Mommy?
What's a meteor?
I can tell you. I have my encyclopedia.
Of course.
Let's see. A meteor is a small piece of rock that enters the Earth's atmosphere and burns up as it falls.
Could this meteor be our new hypothesis?
No, I don't think so. We had a tremor, but not a fireball.
Maybe we just didn't see it.
It says in my notes that it was a cloudy day here. That's right. Virginia Tech reported seeing a fireball, but they also said it was a clear day.
I wonder if a meteor could travel faster than the speed of sound.
If it did, then it could cause a sonic boom, just like an airplane.
And we learned that sonic booms can cause tremors.
That might work. Let's word the hypothesis like this. If a meteor or a fireball is moving faster than the speed of sound, then maybe it can form a sonic boom that causes the tremor.
I think we really need to look into the meteor as the possible cause. We just talked to JPL. Let's call them again. Okay.
Hi, Mr. Balke. It's neat that you actually have a meteorite named after you.
Yeah, we're a little confused on what a meteor actually is. Isn't it the same thing as a meteoroid and a meteorite?
I'm glad to help you. Actually, I had an asteroid named after me. It's easy to get them confused. Meteoroids are small pieces of a rock from an asteroid or comet drifting in outer space. When a meteorite enters into the Earth's atmosphere and burns up, it's called a meteor. People often see these meteors and call them shooting stars.
People near us reported seeing a fireball. Is a fireball like a shooting star?
Yes, a fireball is a name given to a particularly bright meteor. They are sometimes so bright they can be seen in the daytime.
What's a meteorite?
Most meteorites burn up completely when they enter into Earth's atmosphere, but if it's large enough and survives and impacts the Earth, it's called a meteorite, such as the one I'm holding here. Some meteorites can cause craters, such as the one in Meteor Crater in Arizona.
We understand that a fireball was sighted near our town and that it may have caused a sonic boom. Is this possible?
Yes, if it's large enough. The larger size will allow it to last longer and penetrate deeper into the atmosphere. The sonic boom is caused because the meteor is traveling faster than the speed of sound.
Would a sonic boom from a meteor be powerful enough to cause a seismic reading?
Yes, a seismometer will detect a sonic boom from a large meteor. However, to hear the sonic boom, you have to be relatively close, typically within 50 miles or so, and the fireball is visible as far away, 500 miles away.
I would love to see one.
Most fireballs are not observed because 75% of the Earth is ocean, and there aren't too many people in the middle of the ocean. In July of 2001, there was a fireball that was seen from Virginia to Ontario, Canada, and sonic booms were reported by people stretched over an area of more than 100 miles.
This has been a lot of help, Mr. Balke. I think we found the answer to our mystery.
Dr. Peter Brown at the University of Western Ontario is an expert on fireballs. You might want to send him an email and ask him some more questions.
Thanks so much. I'll send Dr. Brown an email.
Wow, I didn't know there could be sonic booms from meteors.
We talked about sonic booms being the answer.
But not sonic booms from a meteor.
Hey, you guys, I just got an email from Dr. Peter Brown. He said it would take a meteor of several hundred kilograms, or the size of a small chair, to equal a sonic boom large enough to be recorded on a seismograph.
Look at this. He also says that if a meteoroid is large enough, has enough energy, and travels deep enough into the atmosphere, then it can cause substantial shaking of the ground and windows. I think this is it. We might have the answer.
I wonder what Dr. D thinks about this. Let's go see him.
Okay.
Hi, Dr. D.
Hi, guys.
We think we solved our problem.
Great. Was it an earthquake?
We're pretty sure that wasn't an earthquake. We think that we have proof that it was a sonic boom produced by a meteor.
A meteor? How did you come to that conclusion?
It wasn't easy. Tony kept insisting that it was an earthquake, but I knew the whole time that it was a sonic boom.
Not really. We dismissed the sonic boom hypothesis in the beginning because generally planes don't fly that fast over land anymore.
In the end, we came back to the idea of a sonic boom when KSNN reported that a fireball had been seen around the same time the vibrations were felt.
When we heard that the people at Virginia Tech saw a fireball, heard a sonic boom, and recorded seismic readings just moments before we did, it just didn't register that a meteor could be the answer.
That's because it was overcast that day and we didn't see a fireball.
Who would have thought it would be a fast-moving chunk of rock? Would you think?
Then we talked with some experts who told us that meteors can cause sonic booms.
Well, it sounds like you've learned several important things. You've learned not to dismiss a hypothesis too quickly like you did with the sonic boom hypothesis.
Yes, and Virginia Tech practically gave us the answer, but we didn't even consider it.
Sometimes the answer is right in front of you, but you just can't see it. The problem is you haven't completely solved your mystery.
We haven't? Well, what do you mean? We have lots of evidence.
We knew it wasn't a construction blast.
And we ruled out earthquakes for a number of reasons.
We also eliminated thunder because there weren't any lightning strikes that day.
So Dr. D, isn't our fireball explanation the best one?
Quote, the greatest detective of all time, Sherlock Holmes. Eliminate all other factors, and the one that remains must be the truth.
Isn't that what we did?
Well, I guess we didn't completely rule out earthquakes.
You have shown that a fireball can cause a sonic boom, that a fireball was seen elsewhere, but you don't yet have enough evidence to really prove that the fireball caused the vibration you felt. In science, you quite often go with the best explanation, even though it's not proven beyond question.
All who agree that this is the best explanation, say aye.
Aye.
You might have hit a lot of dead ends, but along the way you've learned a lot about earthquakes. Sometimes the journey is just as important as the destination.
So you mean what we learn along the way is as important as reaching a conclusion?
Something like that. Congratulations.
Oh no, it's happening again.
You guys feel that?
Yes.
Get off the long sonic boom.
Watch the boom, Kathy.
Is that you, Franklin?
The NASA Science Files was made possible through the generous support of Busch Gardens, SeaWorld, and NASA Langley Research Center's Aerospace Vehicle System Technology Office. Captioning provided by NEC Foundation of America.